So what I'm going to be talking about today is I'm going to be trying to synthesize a lot of this knowledge that we've gained about the physical climate system. And for the purpose of that will be so that you can summarize the logic of why scientists think humans are responsible for the warming that we've seen since the Industrial Revolution. So this picks up very nicely from the John Oliver video, where he talked about a statistically representative debate between scientists that believe that humans are causing the current warming and those that do not. And so the statistically representative debate was between 97 scientists that were for humans causing the current global warming and 3 against. And so that is, that 97% consensus is a number that does show up a lot. And it is grounded in scientific studies. So that number itself is grounded in scientific studies. So this is one of them and one of the most prominent of those, that when there's surveys done, not only of scientists, but of the scientific literature, and you can take raters of abstracts and have them decide what the abstracts are saying, you get this kind of consistent number that comes out that about 97% endorse the consensus position that humans are largely responsible for the warming that we've seen since the Industrial Revolution. So this paper in particular is called Quantifying the Consensus on Anthropogenic Global Warming in the Scientific Literature. And the important sentence in the abstract here is that among abstracts, so they're looking at all of these scientific abstracts, scientific papers, they look at 12,000 papers from the 20 years before this study came out. Among abstracts expressing a position on AGW, which is anthropogenic global warming, 97.1% endorse the consensus position that humans are causing global warming. So it's useful, I think, to think about exactly what that 97% applies to, because there's lots of controversial issues still in climate science, but what's not very controversial is that humans are causing warming. So if we go to this, my topic diagram, the 97% applies to this part, that humans are emitting greenhouse gases, both through burning fossil fuels and through changing land use and their agricultural practices. Those greenhouse gases are building up in the atmosphere, and that is causing the Earth to get warmer. When you start moving further downstream, when you start looking at the impacts on various things like tropical cyclones or droughts, then you're not going to get a 97% consensus on those types of things. It would be less. And then if you go even further downstream, you're talking about impacts on human systems like agriculture, for example, then you would get less of a consensus. So it would be more controversial. And then it would be much more even controversial when you start talking about policies. What exactly is the best policy for dealing with climate change? So just an example for like agriculture is one of those things where we've only seen agricultural yields increase over time. And so if you are trying to attribute some negative impact from climate change to agriculture, you have to really be kind of splitting hairs with, well, they would have increased more had there not been this increase in temperature, that type of thing. So you can just see where it becomes much more complicated. There's more room for debate in those types of things that are downstream. But the 97% consensus does apply to this change in global average temperature. So the class learning outcomes for today, I'm basically going to go through the logic behind why there's this 97% consensus that humans are warming the planet. And so now we're just going to kind of use this and think about the logic and think about everything that we've learned so far in my portion of the class and use that to summarize why scientists think humans are warming the climate. So the first thing is just this fundamental physics that we've been talking a lot about. So there's going to be 6 points here, and I'm just going to fill up this slide with notes, and that will be like one way of summarizing this, but then I'll go through each one of the points individually. So fundamental physics tells us that increasing greenhouse gas concentrations in the atmosphere should warm the surface of the planet, all else being equal. And that's often an important caveat in science. You're trying to isolate one thing. So if you don't change anything else, then changing greenhouse gases should warm the climate. And this is like not something that emerged recently. This is very, very fundamental physics that was first proposed way back in the year 1824. So this is Joseph Fourier proposed the existence of the greenhouse effect in 1824. And he was doing this largely, basically through theory, that he was thinking about this diagram that we've been talking about in this class of how much energy is coming in from the sun and how much would be reflected away. And he was making these calculations of what the surface of the planet should, what the temperature of the surface of the planet should be. And he was getting numbers that were way too cold. And so he said, you know, maybe the atmosphere actually inhibits the energy leaving, and that's what causes the Earth's surface to be as warm as what we actually observe. So he, I guess, yeah, so he had, you know, observations obviously of how the world is, and largely kind of just came up with this theory of, okay, the atmosphere must be inhibiting the amount of energy leaving in order for the surface temperature to be as warm as what we actually observe. So that's pretty cool that just through kind of thinking about it, he came up with the right answer there. And so then this progressed through the 1800s. So a couple decades later, John Tyndall was the first person then to kind of take that theory, and he was the first person to show the heat trapping property of certain gases that we ended up calling greenhouse gases. And then a couple decades later, this guy Arrhenius published the first research on carbon's effect on surface temperature. And then in the 70s and 80s, current global warming, the warming that we've seen over the past 40, 50 years, was predicted before it was actually observed. So that's crucial, because that's an experiment on kind of the whole planet of saying, if we continue to increase greenhouse gases, then we expect global temperature to increase. That's a prediction, and that prediction came true. I like to show this actual paper from 1896, just because I think it's pretty interesting. So here's a paper, April 1896. It's called On the Influence of Carbonic Acid in the Air Upon the Temperature on the Ground. And even then, he says, a great deal has been written on the influence of the absorption of the atmosphere upon the climate. So like he's already saying, like, this is this kind of well-established thing that there's this greenhouse effect that John Tyndall was talking about, you know, in the 1860s. So it was a long time before him. And yeah, so the point here is just that, like, this physics of the greenhouse effect emerged kind of with physics in general, and is not some new thing. There's been just tons and tons of science accumulated on it. And the fact that so much science has accumulated on it for so long just makes it much less likely to be wrong. So Tyndall had these apparati for figuring out how gases interacted with different wavelengths of radiation. And we can largely reproduce these experiments pretty easily. So this is a video of that. So here's just an experiment that's very similar to what they were doing in the 1800s.
I can show you how carbon dioxide affects Earth's climate using this heat-sensitive or infrared camera, which is purring away here, and a candle, this glass tube, which is hooked up to this rather large canister of carbon dioxide gas. Now, if I light the candle, you'll see that on the monitor, the camera picks up the flame perfectly. Look at that. The hottest parts are glowing white. Now watch what happens when I turn on the carbon dioxide.
Just keep your eye on the flame.
The gas is invisible, so you don't see it fill in the tube. But as it comes in, you should see the candle start to disappear. There it goes. Look at that. What's happening is that the carbon dioxide in the tube is effectively trapping the heat.
The candle's warmth no longer reaches the camera. Instead, it's absorbed by the carbon dioxide inside the tube. That's exactly how carbon dioxide works in the atmosphere. It traps heat.
So I think this is like the crucial frame here, that the camera, keep in mind the camera is an infrared camera. So it's seeing only in the infrared, not seeing in the visible. And so when the carbon dioxide goes in here, you can't see it fill up with your eyes, right? That's what makes it a greenhouse gas. It does not interact with the shortwave radiation. So it'd be much more complicated if you put carbon dioxide in here and it turned pink, like a pink cloud or something, because then that would mean that it is interacting with shortwave radiation, and it wouldn't be clear how its effect would be on the surface temperature. But when you fill it up, you can't see it with your eyes. But the infrared camera that's only seeing long wave radiation, all of a sudden loses, it can no longer see the candle. So what it essentially is happening is you got the camera looking at the candle in the infrared, and so it can see that infrared radiation coming off of the candle. Obviously, the candle is also emitting shortwave radiation that we can see with our eyes. But then when you put CO2 in the container, then the camera can no longer see the candle because the CO2 is absorbing that and it's re-emitting it in all directions. But that kind of emission in all directions means that you can't exactly see the flame anymore. And so that's just an experiment that anyone can do very easily, that's not too expensive, and it's something that was essentially what was done in the 1800s to first kind of realize that, oh, different gases are interacting with different wavelengths of radiation differently. And so maybe these gases are causing the Earth to be warmer than they would be if we didn't have those gases in the atmosphere. So that's one, is just our fundamental physics of the greenhouse effect. So we know that we have this greenhouse effect on Earth. And then there's just kind of this next step in the logic is we know that through burning fossil fuels, humans have increased the concentration of greenhouse gases in the atmosphere. So when we look at ice cores and things like that, we see that CO2 concentrations were pretty much constant for thousands of years, and then have increased by about 50% since the Industrial Revolution. So this is just connecting those dots that we know humans are putting CO2 into the atmosphere. So this is our annual emissions of CO2 by country. So basically 0 in 1850, not that much still, in the early 1900s. And it's really post World War II that we explode in our emissions of CO2. And so the emissions are the flux going into the atmosphere, and the concentrations are how much is in the atmosphere at any given time. And so, big surprise, when you start putting more of these gases in the atmosphere, they start accumulating, and you actually can measure that there's more of those in the atmosphere. So this eliminates any possibility that the increase in CO2 is natural. That would just be the most profound, ridiculous coincidence in the world, that it was steady for a very long time. And then once we started putting CO2 in the atmosphere, it spiked up for some other reason. It doesn't make any sense. So we know that the increase in CO2 in the atmosphere is due to fossil fuel burning. And similarly, we know that nitrous oxide and methane going up in the atmosphere is due to human activity as well. So we know that we have a greenhouse effect. We know that humans are putting more greenhouse gases into the atmosphere. And then the physics of the greenhouse effect says that we should observe warming with that. And we have observed an increase in global surface temperature. And the amount of the increase in global surface temperature is exactly what we would expect, given the amount of greenhouse gas concentration that we've seen go up, or how much they've gone up. And given just our first law of thermodynamics that we've been talking about, that we know that a change in temperature has to do with a change in the Earth's energy budget. And so then you do have to make this correction for the fact that humans are also causing some negative radiative forcings, or some cooling that offsets some of the warming that we've seen. But we've seen an increase in global surface temperature, and you saw in my recorded video last time all of the different pieces of evidence showing that the world is warming. So we can see it through direct measurements, thermometers on the ground, and sea surface temperatures measured from buoys and floats and ships. We can see it from weather balloons. We can see it from satellites measuring the temperature of the atmosphere. We can see it in all sorts of different parts of the cryosphere. So reductions in ice in alpine glaciers, reductions in sea ice, reductions in size of the ice sheets, and then other kind of indirect lines of measurement, like species moving poleward and upward, the time of year when a lake freezes over, those types of things. Basically, everything is showing that the Earth, on average, is getting warmer. So it's not just reliance on one piece of evidence. And it's like exactly the amount of warming that we would expect. So this is a graph of using a simple model and simple theory combined with observations. That this is the observed land average temperature in black here, going back to 1750. And then this is like a simple kind of first order explanation for what we would expect temperature to do if the only causes of temperature change were changes in CO2 concentrations and changes in volcanic eruptions. So these big dips down here are explained by big volcanic eruptions that cause cooling for a period of time. But then the long-term increase is caused largely by CO2 and other increases in greenhouse gas concentrations. And so like any deviation of observations from this red line is not explained by these two variables, so it would require some other explanation. But we can see that a lot of the variability is explained by just those two variables. And so in particular, the long-term upward trend is explainable by this increase in greenhouse gas concentrations. And so I think one of the most powerful pieces of evidence for that is that it was actually predicted beforehand, the increase that we've seen recently. So it's often said in climate science, like, we wish we had a whole second Earth to do experiments on, because then we would be able to know for sure that there are various causes of things. And so we have to resort to climate models to do that experimentation. But really, we have done the experiment. because before the warming that we've seen, recently, there were papers predicting that that should be the case. So that kind of is an experiment on the whole planet. So this is an example of that. This is a paper from 1975, published in Science, one of the most prestigious scientific journals. And it's called Climatic Change, Are We on the Brink of a Pronounced Global Warming? And so it says if man-made dust is unimportant as a major cause of climate change, so he's talking about aerosols, like the sulfate aerosols that cause cooling, then a strong case can be made that the present cooling trend will, within a decade or so, give way to pronounced warming induced by carbon dioxide. Actually, this paper was like the first to popularize the term global warming, so that's why that term became kind of the shorthand for climate change. But this is very interesting because there, again, it's not backcasting. It's not saying, okay, we've observed warming, let's come up with explanations for why that's the case. It's based on, like, we know the physics of the greenhouse effect, and we know that CO2 is a greenhouse gas, and we know that we're putting CO2 in the atmosphere. So even though we haven't observed much warming so far, we should see that in the future. And then that is, what actually came true. I have another example of this experiment. This is a video. Okay, so here is global temperatures and CO2 concentrations. And I'm making this point that global temperatures should rise with CO2 concentrations, but just because they correlate doesn't mean there's a causal relation between the two things. And it's much stronger evidence if you can make a prediction and see whether or not that comes true. And so here I'm going to show you a prediction from a paper around the same time period as that other one, except this is like 1981, so 6 years later. This is from James Hansen, who has been one of the most famous climate scientists of the 20th century anyway. He's not as prominent now, but he very famously gave testimony in 1988 before the US Congress that really brought climate change into the public consciousness. So he has this paper also in Science called Climate Impact of Increasing Atmospheric Carbon Dioxide. And this is what the global temperature looked like at that time. So again, they're ahead of the curve here. And they show this graph in the paper, so I've just overlaid our estimate of temperatures updated on top of this. But so what they're showing here is, okay, here's observed temperature from 1950 to, when the study was starting to be conducted in the late 70s. And they put on here, essentially, their hypothesis test. So they're saying that if CO2 is not causing temperatures to rise, then we would expect the global temperature over the next, through 2020, so through present, to stay within this envelope. So just kind of go up and down within this envelope. But if, like all of physics tells us, if CO2 does cause the Earth to get warmer, then we expect temperatures to emerge out of this envelope in the 1990s about, and then increase and get further and further away from this envelope over time. And then what actually happened was this. So the Earth ended up warming a lot more than even they were showing. And so it kind of emerged out of this envelope very quickly after this paper was published. And there's some reasons for that. I don't think they got the actual emissions right. It wasn't so much that the climate sensitivity was wrong or how much warming you get for a given amount of CO2 increase. But this is showing, again, that they set up the experiment with the whole world and tested, and then we ended up testing the hypothesis that CO2 should cause global temperatures to increase. And the test reveals that they do. And so that's predicted ahead of time and much more powerful than trying to backcast something or trying to come up with an explanation after you've seen the observations. Okay, so those are just kind of like basic logic and things that we've talked about before. We haven't talked about this one previously, but this is another piece of evidence that the warming that we've observed is from increasing greenhouse gases, and that is the spatial uniformity of the warming. So that means, like, in space, spatial uniformity, like the same. So that it's warming more or less the same over the whole globe. And that is what we would expect if the cause of the warming was from these well-mixed greenhouse gases like CO2. So this is just a visual depiction of that spatial uniformity. So it's not totally uniform. There's changes in the rate of warming. This is the trend in warming from 1880 to 2020. And we see that it's warming a little bit faster in the high latitudes in the Arctic, and it warms faster over continents than over the ocean partially because of the lower heat capacity of the continents compared to the ocean. And then there's a location in the North Atlantic, where there's actually cooling. And we think that might have to do with an ocean circulation changing strength there and affecting less heat into that region. But overall, it's warming more or less everywhere. And that is what we would expect if the warming was caused by something like CO2 that's just well mixed in throughout the whole atmosphere. Like we talked about, that CO2 just accumulates and it's mixed globally. And so China's emissions are mixed with our emissions, or mixed with India's emissions, or mixed with Europe's emissions, or mixed with Australia's emissions. They just all accumulate in the atmosphere. And so that should be causing global warming. If it was something else, if it was something like, there was a change in the way that the atmosphere is moving heat around, and that caused ice to melt in Siberia, and so that caused there to be more absorption of solar radiation in Siberia, then that would be a different map. That would be like, okay, it's warming a lot more in Siberia than in other locations, and you'd be able to see that. And so that, some type of other exotic explanation would look differently. It wouldn't be the spatial uniformity that we see here. And there's also uniformity in the vertical, where we see both the atmosphere warming and the ocean warming. So that eliminates any type of possibility of there just being like an exchange of energy between different locations. So we talked about that, like, we're conserving energy, we're not creating or destroying energy, but you could, come up with some explanation of like, well, maybe the surface temperature where we live on the surface, that's getting warmer, but it's at the expense of heat from the ocean. So maybe like heat from the ocean is moving up to the surface for some reason, and that's why we observe temperatures increasing at the surface. But this eliminates that because the ocean is warming as well. So it's not just some exchange of heat between those two things. If the ocean is warming and the atmosphere is warming, and it's warming over the whole spatial extent of the planet, that means that it has to be coming from that top of atmosphere energy budget that we've been showing, the incoming shortwave radiation, the reflected shortwave radiation, and the outgoing longwave radiation. And again, that reflected shortwave radiation like really can't be that, because there's not some reflected shortwave radiation that's like globally distributed like this. It's, there's ice in certain locations, and clouds are not distributed uniformly like this. So it really just points to it being due to increases in greenhouse gas concentrations. So in addition to that piece of evidence, we can also actually directly measure the greenhouse effect being enhanced, both through satellites looking down at the Earth and through stations at the surface looking up at the sky and measuring long wave radiation coming back down towards the surface of the planet. So here's just an example of some papers that have done that. There's a lot of kind of scientific jargon in here, but it's pretty simple based on what we've talked about with this energy budget. That this is a paper called Radiative Forcing Measured at Earth's Surface Corroborate the Increasing Greenhouse Effect. And what they're doing is they have a bunch of stations on the surface of the planet. They are looking at this component of the energy budget, the long wave radiation coming back down, and they're saying it's increasing. They're saying the resulting uniform increase in long wave downward radiation manifests radiative forcing that is induced by increased greenhouse gas concentrations and water vapor feedback, and proves the, quote, theory of greenhouse warming with direct observations. So we see more of this radiation coming back down towards the surface of the planet. So it's a direct measurement of an enhanced greenhouse effect. And this is a plot of all those surface stations that they looked at over most of the planet. You see this increase in this component. And so since we conserve energy, then we should also see a decrease in outgoing long wave radiation at the same time that you're seeing an increase in radiation coming back down towards the surface. And that's what this is an example of a paper showing that, called Increases in Greenhouse Forcing Inferred from the Outgoing Long Wave Radiation Spectra of the Earth in these 2 different years. And so basically they're just comparing what was leaving the Earth at 2 different time periods when CO2 was different, and showing that our results provide direct experimental evidence for a significant increase in the Earth's greenhouse effect that's consistent with concerns over radiative forcing of climate. So they're saying this has decreased over that time period, which is exactly what we would expect. And you can even go in more detail, because different greenhouse gases interact with different wavelengths of radiation differently. You can look at like specific wavelengths to see like what greenhouse gases are causing what, and figure out the radiative forcing of each one of these greenhouse gases. So this is just an example of how the greenhouse gas CO2 and the greenhouse gas water vapor H2O interact differently with different wavelengths of radiation. So this is 10 micrometer wavelength. This is 1 micrometer wavelength. And this is how much of that radiation they absorb. And so like if you can see here, if you have a satellite looking at wavelengths of 4 micrometers looking down, and you see that radiation decrease, then you know that's because of CO2, because water vapor, this is showing water vapor does not absorb at that wavelength, but CO2 does. And so if we see a decrease in 4 micrometer radiation, then that's due to CO2. So the only point there is just that like we can be very detailed in what's actually altering the Earth's energy budget by taking advantage of the fact that these gases interact differently with different wavelengths of radiation. This is another paper just basically doing the same thing using satellites and surface observations. Here's their kind of headline. These results confirm theoretical predictions of the atmospheric greenhouse effect due to anthropogenic emissions. And they have a graph in here showing CO2 radiative forcing over the time period that they looked at. So it was, when they had observations available from 2000 to about 2015, and they're just showing the radiative forcing that we've been talking about. So it all makes sense. It all kind of comes together, that we have this, we know the fundamental physics of greenhouse effect. We know humans are increasing greenhouse gases. We know that surface temperatures are increasing exactly, in line with what we would expect given the increase in greenhouse gases. We know that surface temperatures are increasing in a way that makes perfect sense if it was caused by increasing greenhouse gases. And we can actually measure the greenhouse effect itself increasing, not just indirectly inferring that the greenhouse effect is getting stronger because temperatures are increasing. We're directly measuring the greenhouse effect increasing. And so then the last piece here is, what about natural climate changes in the past? And so this piece is basically, there is no satisfactory natural explanation for the warming that we've observed since the Industrial Revolution. There's kind of two subpoints to that. One is that many previous climate changes were actually affected by CO2. So CO2 has been very important in previous climate changes, but the kind of drivers or the causes of these CO2 changes, an example would be changes in the Earth's orbit, are too slow to be responsible for the warming that we've seen since the Industrial Revolution. So we see a lot of climate changes in the past, but the climate changes of the past, oftentimes we're talking about, at least tens of thousands of years timescales, often hundreds of thousands of years, often millions of years. And so those are just they're not moving fast enough to cause a pronounced warming over 100 years. And then the second point is that changes in volcanic activity and solar radiation can cause changes in global temperature on decade to century timescales, but they have not been moving in the direction that should have caused warming over this most recent period of time. So I just have a couple graphs just extrapolating on that a little bit. That there's been a lot of natural climate changes in the past. A lot of those have to do with very slow things like geologic changes, changes in the position of the continents, which move at about the pace that fingernails grow, and so they move very, very slowly. They're not going to be changing on the timescales of 100 years. Then there are changes in Earth's orbit, which have had very, very important changes in the climate. But even those are like 10,000 years. They take tens of thousands of years to really affect the climate. So those are too slow as well. So most of what we've seen in the past can just be eliminated because of the time scale. And then what can't be eliminated is this solar and volcanic activity. But we've talked about these already. So this is what those radiative forcings look like over this time period since 1750. And so we know for sure what the solar radiative forcing is recently because we have satellites directly measuring it, and we can kind of infer it back previously through evidence in the environment. There's certain isotopes that vary with solar output, and there's also the fact that people have been counting sunspots forever, and so we kind of know the correlation between how many sunspots are on the sun and how much radiation is coming from the sun, and so we can reconstruct it that way. So basically, we know that the solar radiation has been relatively flat, and we know that there have been major volcanic eruptions that have caused short-term cooling, but those are really kind of deviations in the cooling direction that then the planet can recover from. They don't cause long-term warming. And so when we put these radiative forcings in the models, as I've shown, this is what the temperature, what we think the temperature would have done, or the envelope that the temperature would have been in if humans had not been increasing greenhouse gas concentrations. And so this looks very similar to that James Hansen 1981 paper of this is the envelope that we would expect temperatures to stay in if we weren't increasing greenhouse gas concentrations. But observations have shown that we've emerged from that, and we can basically put it together, that we know the components of temperature change that have resulted in the observations being the way that they are. And so we can also eliminate solar and volcanic activity. And so then that's the summary, is that there's no satisfactory natural explanation. And if someone did come up with a natural explanation, they would also, the burden would be on them to say, well, why would CO2 not have caused the warming, given what we know about fundamental physics, and given that we know that the concentrations of greenhouse gases have gone up, given that we can measure the enhanced greenhouse effect? Like if someone came up with some alternative natural explanation, they would also have to basically explain why all of this stuff is wrong as well. And so that's just it's a hurdle that's so high that it's basically considered as close to a fact as we can get, that humans are causing basically all of the warming that we've seen since the Industrial Revolution. You kind of split hairs a little bit about like maybe there's some internal natural variability that's caused part of this recent increase that isn't fully attributable to greenhouse gases, but our best estimate is that all of the warming is due to human caused increases in greenhouse gas concentrations.